Hi there. We are going to talk today about just the beginning of section 6.2, which is called transforming and combining random variables. And today we're going to focus just on the transforming part. And this is going to feel like a lot of review because it is. We have done this before, just with raw data instead of thinking about it in terms of a random variable. So let's get started. In chapter 2, we studied the effects of linear transformations on the shape, center, and variability of a distribution of data. Meaning, if I have a set of data, for example, something like 1, 2, 3, 4, 5. So if that's my set of data, I could say, the mean is 3, the median is 3. I could find the standard deviation, the IQR, all this stuff. I could say that it's symmetric, uniform, whatever. If I did a linear transformation on this data, for example, if I added 3 to every value, so adding 3 to every value would make my new data set 4, 5, 6, 7, 8. We talked about, that's what a linear transformation is. We talked about the effect that adding 3, multiplying by 7, whatever, would have on the center, shape, and variability. So quickly to review in chapter 2, kind of our rules that we came up with. If we added or subtracted a constant to each observation, in other words, if I added 3 to every single data value, or subtracted 5 from every single data value, it would add or subtract that same value to the measures of center and location. Things like mean, median, things like minimum, maximum value. Although it would not change the variability. Remember, we said adding 3 to a set of data, when you add that 3, you still have this, the variability, like the spread, the range, the standard deviation, the IQR is still going to stay the same. And it also doesn't change the shape or measures of variability. Sorry, that's repetitive. So how about multiplying or dividing each observation by a positive constant b? So instead of adding 3, if I took each data value, let's say I had, again, 1, 2, 3, 4, and 5. And if I multiplied each of these by 2, I would have 2, 4, 6, 8, 10, right? So it's, again, is going to change the measures of center and location. So in this case, my mean, my median, my maximum, my minimum, all those numbers are also multiplied by 2. But it also changed the spread of the distribution. So my data is now spread out. Look, even if I just think about range, in red, my original data, the range went from 1 to 5. Now, my range is going from 2 to 10. So it's twice as big, right? So it changes your IQR. It changes your standard deviation, your range by a multiple of 2. Although it does not change the shape of the distribution. So those were our rules on like the raw data values, right, from chapter 2. Now we're basically going to kind of look at the same thing, but we're going to apply these rules to random variables. So if you have this intro to rules of random variables packet, we're just going to look at page 1. So if you want to kind of go through this on your own, it might be helpful for you to think about this independently. You can pause the video and then kind of like fast forward through what you don't need or whatever, but I am going to step you through step by step in case you did have some questions. All right, so here we go. I have a random variable A and its probability distribution. So first thing, I asked you to make a histogram of the probability distribution. So if I were to make a histogram, I would start with the values of A, and here's my number line, 1, 2, 3, 4, and my probabilities go over here. And so my maximum probability goes up to 0.4. So I'll make this like 0.1, 0.2, oh, I didn't scale this well, did I? 0.3 and 0.4. And then my bars, I would have a bar at 1. I would have a bar at 1.5. I would have a bar at 3. And then a bar at 4. Not perfect, but you kind of get the gist. Now, to find the mean and the median, the variance, standard deviation, range, all that stuff, you're going to go to your calculator. You're going to type this into L1 and L2. And I'm also going to show you how to make this histogram in your calculator as well. So if I go into Stat Edit, keeping in mind I put the data values of the random variable here. So the values of the random variable are 1, 1.5, 3, and 4, and then each corresponding probability in a separate list. How do we make a histogram? We have our data in the list. We go second stat plot, make sure it's turned on, and I'm going to scroll over, select histogram. Now before, if we just wanted a histogram of a bunch of data values, we would just hit graph or zoom 9, whatever it is. But now we have a random variable, and my data values in L1 are now weighted on the probabilities in L2. So I'm going to scroll down to frequency, change that from 1, and I told you in the beginning of the year, don't change that, don't ever change it. Well, now we're changing it. So change that to L2 because we're weighing L1 on L2. And now you could zoom 9 this, but I'm going to show you. I actually set my window. Here's what I set my window to, and you're just going to, if you want to follow along, just trust me on this for right now. You'll see why later, why I did this. But I go from -1 to 10 in the X direction just so I have plenty of room to see, you know, here's my X values 1 through 4 for now. And then my probabilities have to go from 0, they're going to be between 0 and 1, right? And so I just went a little bit further in the y-axis in either direction just so we could like kind of see what was happening. So here when I graph it, ta-da, it's kind of like probably a nicer version of what I did there, right? So if we wanted to find the mean, the median, standard deviation, just as a quick reminder, I'd second quit. Stat, calc, one variable statistics. My data is in L1 and I want it weighed on L2. I hit calculate and here's everything that I need. So I'll scroll down so you can kind of check what's in your calculator matches what's in mine. And then in terms of notation, I'll help you practice writing this down. So remember, when we talk about the mean of a random variable, we have a population. So we're going to use mu, but we use mu sub a to indicate that it's the mean of a random variable a, not just the mean of a population. So it was 1.85, and we can interpret that. We're not going to. We've gotten good at that in the last section. The median. So there's not really a fancy notation. I'm just going to write the median of the random variable a was 1.5. So the variance, remember, variance is the standard deviation squared. So they only give you in the calculator, they only give you standard deviation, right? Here's your standard deviation. So you're going to have to, in order to answer this question, you're going to have to type into your calculator 0.90967 squared to come up with the variance, right? So my variance ended up 0.827. My standard deviation of A was 0.910. And my range was just 4 minus 1. I don't need the calculator for that, but that gave me 3, right? All right, perfect. Old news, we know how to do that. Moving on. Now we're going to define the random variable B to be equal to A plus 3. So make a probability distribution table and a histogram of B, and you're going to see these questions are really repetitive. So, all right, I'm adding 3 to each of my possible outcomes for A. Well, here's A, right? If I add 3 to each possible value, 1 plus 3 is 4, right? 1.5 plus 3, 3 plus 3, and then 4 plus 3 is 7. So these are my new possible outcomes. So all the possible outcomes for B, I take all the possible outcomes for A, that's these, and I add 3 to them, right? But they each occur with the same original probabilities. So the probabilities haven't changed. The probabilities of each outcome haven't changed, just the outcomes themselves, right? Let's make a probability, or I'm sorry, let's make a histogram. That's my probability distribution table. Let's make a histogram. So now here's B. So if this is 0, 1, 2, 3, 4, 5, 6, 7, right? And these are my probabilities. So this will be like 0.4, 0.2, just to make it a little quicker. So 2, 4, 6, 8. All right, perfect. So my histogram, I need a bar at B equals 4 that goes up to 30%, 4.5 that goes up to 40%, 6 that goes up to 25%, and again, this is not perfect, but 0.05, there you go. So what does this look like? It looks very similar to what we saw before, right? And it should. Now, let's get into the calculator, and I'll show you how to use this calculator a little bit. So to find B, we want to take A minus 3. If I go into Stat Calc, we know how to use these formulas in the list here. So, I mean, you can pretty easily type that 4, 4.5, 6, and 7 values in. But I could also type in L1 plus 3, hit enter, and it fills those values down. And so now I want to make a histogram, find the mean, median, variance, blah, 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 of all these values in L3, and I still want to weigh them on L2, right? They each still have the same probabilities. So let's go into second stat plot. We'll go into plot 2. We'll turn it on. We'll go select a histogram. But now my new X values, or like in this case B values, they were in L3, and I still want to weigh them on what was in L2, right? When I graph it, look what happens. And you can tell this from your paper, but the shape, it was like the same histogram, it's just shifted along the x-axis. Well, specifically how? It shifted 3 units to the right, because I added 3 to each of those A values, right? Hopefully that kind of makes sense. Now, if I want to find the mean, median, all that stuff, I go second calc, one variable statistics, and now I'm looking for the mean and median and whatever of everything that's in L3 weighed on L2, right? Using the same probabilities. So now here's my new mean, standard deviation, min, median, all this stuff, okay? So let me fill this stuff in for you, or help you write this down. Again, using our notation. So the mean of the random variable B was now 4.85. The median of the random variable B, 4.5. The standard deviation, 0.910. So I have to type that into my calculator to get the variance, 0.827. And now the range of B is the max minus the min, which is 3. Right? So kind of in summary, take a minute, pause the video, and think about how can I compare my answers for random variable A to my answers about the random variable B. And these answers should feel really similar, like I said before, to exactly what happened in chapter 2. So what happens with the raw data happens again when we're adding or subtracting a constant to a random variable. So the measures of center, we add or subtract that constant. So look at the mean. The mean of A was 1.85. The mean of B, 4.85. So 1.85 plus 3. Look at the median, the same thing for the median. Look at the max value. Look at the minimum value. But now look at question number 8 here. It says compare your answers to questions 3 and 6 above regarding measures of variability, the variance, standard deviation, range. Did the ranges change? They didn't change at all. And why? Think about it. If I'm adding 3 to each data value, I'm shifting them along the x-axis to the right, in this case if I'm adding, or if I'm subtracting to the left, but I'm not changing the variability. I'm not spreading them out anymore or condensing them at all. So my measures of variability stay the same. Okay, so put that off to the side for right now. And let's look at, now that we've kind of established these rules, let's kind of revisit one of these example problems that we've looked at before and apply the rules. So remember Pete and his Jeep tours, right? So C is the total amount of money that Pete collects on a randomly selected trip. So remember, it depends on, I think it was like the number of passengers that he has as to why he would collect more or less on any given trip. So this is old news. We've looked at this before. We made the probability distribution table and the histogram. Now, it costs Pete $100 to buy permits, gas, and a ferry pass for each day trip. So we'll call V the amount of profit that Pete collects on a randomly selected trip, right? So if he charges $300 for the trip, but he has to pay $100, you know, in supplies and whatever else, he's really making $200 per trip. So hopefully these kind of profit values here make sense, right? But each of these profits are now basically subtracted. We subtracted 100 from how much money he collects, but each of these have the same probability of occurring. That didn't change the chances of getting, you know, a $900, for example, trip. It just changed the amount of money that he gets to keep, that he profits from, right? So we're going to call our random variable V, meaning his profit, C minus 100. C was the amount, the random variable was defined to be the amount of money that he collected. So look, I can just shift literally all these histogram values to the left to get this one here, right? How does the distribution of V compare to the distribution of C? The distribution of V has a mean of $462.50, which was exactly $100 less than what we calculated before. And I'm not going to go through all this if you don't believe me. Pause the video, type all these into your calculator and double check. The standard deviation did not change. Our variability is still the same. And the shape was the same as the original shape as well. I would say that that's pretty symmetric, right? With one single peak. All right, so formally kind of like tying this all together, the effect of adding or subtracting a constant on a random variable or a probability distribution. If I add or subtract a number from a random variable, it would add or subtract from all the measures of center and location, mean, median, minimum, maximum, Q1, you know, whatever the value for the 50th percentile, the 75th percentile rank was. Those are measures of location, right? But it does not change the measure of variability. It doesn't make your data any more spread out or like less spread out, right? Or more condensed, whatever. It also didn't change the shape. Exactly the same rules for random variables as we had in chapter 2 for just raw data values. Okay. So let's look at another example. In a large introductory statistics class, the score of a randomly selected student on a test worth 50 points can be normally distributed with mean 35 and standard deviation 5. So note, star, 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 they tell me it's a normal distribution, right? So due to a difficult question on the test, the professor decides to add 5 points to each student's score. Let Y be the scaled test score of the randomly selected student. The key is that he's adding 5 to each student, every single student. If it wasn't every single student, I can't apply these rules. But let's apply these rules. So what do we know about shape? Shape stays the same. So it's still going to be normal. What do we know about center? It shifts depending on whether you add or subtract, right? So if we add 5 points to each student, we add 5 points to the mean. So the original mean was 35. My new mean is now 40, right? But it doesn't change variability. So if the standard deviation originally was 5, my new standard deviation is 5 as well. Okay? All right, back to the packet. Flip over to page 2. So again, like I said before, if you want to pause the video and work through this kind of like independently and then check at the end, feel free. I'm going to go through it step by step. If you want to kind of follow along with me, totally up to you. So we're just working on page 2. We're defining a new random variable C to be A divided by 2. So before we talked about adding and subtracting. Now we're going to look at, well, what happens if I take my values for my random variable and divide them by 2? So make a probability distribution table. So here's A, right? Here's the original values of the random variable A. Now I need to take each of them and divide by 2, and that's going to give me C. Well, what's 1 divided by 2? You can use fractions, you can use decimals, it doesn't matter, it's up to you. 1.5 divided by 2 becomes 0.75, right? 3 divided by 2 and 4 divided by 2. But that doesn't change the probability of each outcome, right? So my probability values are still the same, right? Let me make a histogram. So here's my values of C, here's my probabilities of each C, 0.4, 0.2, and if this is like 1, 2, 3, what are my bars going to look like? So I'm going to have a bar at 0.5 that's going to go up to the C value of 0.5, so that's like right here, that's going to go up to a probability value of 0.3. So like that. Now 0.75 is going to go up to 0.4. I'm trying to squeeze this in. I'm not doing a great job of it, but 1.5 will be like right there, and then 2.05. All right, what does the shape look like? Hopefully this is feeling repetitive, right? Let me go into my calculator. If I go into stat, edit. So to find the values of C, the values of the random variable C, again, I'm going to take all the values of A, which I have in L1, and divide them each by 2. Like I said before, I could just manually type these in, or if you have a longer list, you could just do second L1 divided by 2. Fill that down, hit enter. So it gives me each of those possible outcomes for C now. But I'm still weighing these outcomes that are now in L4. I'm still weighing them on the probabilities that I originally put in L2, right? Let me go up here and make a histogram. So I'm going to go in plot 3, turn it on, histogram. So my values of the random variable C are now in L4. So I'm going to type in L4 and I want to weigh it on the probabilities, which are still in L2, right? And now this one's going to be in green. Look at that. So I'm going to second quit, find the mean, standard deviation, all that stuff. So I'm going to change this to L4. And again, wait on the probability values in L2. And when I hit calculate, this is what I come up with. I'll scroll down a second just so you can compare, make sure we get the same thing if you're using the calculator. All right, I'm going to come back, write this stuff all down. So the mean of the random variable C was 0.925. The median of the random variable C was 0.75. The standard deviation was 0.45. And if I ask you to find variance, you type that 0.45 in, square it, get 0.207. And the range, now the maximum is 2, the minimum is 0.5, so the range is 1.5, right? And let me indicate that that's the range of my random variable C. All right, there's all my stuff. So now I am going to compare these answers for my original answers for the random variable A. So if I flip back to the very front page, the first 3 questions, 1, 2, and 3, and I compare those answers with my answers that I have here, take a look, flip back and forth. What do you see that happens? All right. So the number 12, number 12. When we compare our answers about means, medians for number 2 and 10, you're going to notice that the mean and the median in number 10 is literally the mean and the median from number 2 just divided by 2, right? So we divide or multiply by whatever the constant was. Now, number 13, did our standard deviation, did our range, did our variance, did they change? In this case, now they did change, because when I multiply or divide by a constant, not only am I shifting my data values on the x-axis to the left or to the right, depending, but I'm also either expanding or condensing, the range. So the whole distribution of data, the variability changes. So if I look at the range and the standard deviation, they get divided or multiplied by the constant. But check to see about the variance, or in other words, sigma squared. If I take sigma squared from the random variable A, which was 0.827, right? And if I divide that by 2, because we divided all the C values by 2, do I get my new variance here? I do not. So think about the relationship. If I take my standard deviation value from A, and I'll write these, let me rewrite these down for you so that you can see this a little bit clearer. My standard deviation for A was 0.910, and my variance for A was 0.827, right? So I can see that with my standard deviations, these values here, if I take 0.910 and divide by 2, I get the standard deviation of C, right? But when I divide by 2, I do not get this. Well, think about it. These are squared values. So if I take 2 and square it, I get 4, right? So if I take 0.827 and divide by 4, try it in your calculator, you get this value here. So in other words, you can divide or multiply the standard deviation, but the variance gets divided or multiplied by the constant squared. Okay. Let's take this and apply it to a couple of practice problems. So here, in summary, here's my rules. When I multiply or divide, it multiplies or divides the centers of location, minimum, maximum, mean, median, percentile rank. And it also multiplies or divides the measures of variability, range, IQR, standard deviation. But it still doesn't change the shape of the distribution. So just like in chapter 2. All right, let's look at an example. El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units, call that like credits. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has this distribution. So students are taking between 12 and 18 credits, and these are the probabilities with which each students are taking that amount of credits, right? So now we make the histogram to the right there, kind of like an ugly shape. I would say definitely like has multiple modes, like 3 modes, right? But I would still say it's like relatively symmetric, right? So because it's symmetric, we should use the mean and the standard deviation to measure the center and the spread. All right, perfect. So at El Dorado Community College, we care about the number of credits, but what do I really care about? I care about how much it's going to cost me. So the tuition for full-time students is $50 per unit, or $50 per credit. So that is, if T is the random variable tuition charge for a randomly selected full-time student, T is equal to 50 times X. So 50 times the number of credits they're taking, right? Okay. So, oops, look, my answer appeared. But what shape does the probability distribution of T have? It's going to be exactly the same. It's going to be the same as the original probability distribution of X, kind of symmetric, that ugly shape with the 3 peaks, right? But the center, if I multiply all these values by 50, right? Because that's what T is, taking each of these and multiplying by 50, right? It's going to multiply the measures of center. So the new mean is going to be 50 times the old mean. In other words, $732.50. So if I randomly select a full-time student at this college, on average, they would be paying approximately $732.50 for their, I guess full-time tuition this semester. Variability, multiplying by 50, also multiplies the original variability. So here's my my standard deviation value. All right, kind of like tying things up. A linear transformation is when you take a random variable and you can add or subtract a constant and multiply or divide by a constant. So it's like the combination of both of those things. one or the other or both, either adding, subtracting, multiplying, or dividing, or doing a combination of those things. So we know that the mean is affected by what you multiply by and by what you add. On the other hand, the standard deviation is only affected by what you multiply by. But we also know the shape doesn't change no matter what you do, if you're adding or subtracting, multiplying or dividing. So that tells us about shape, center, spread, right? Just keeping in mind, these results apply to both discrete and continuous random variables. So we saw discrete random variables with like Pete's Jeep tours. That was discrete. We applied the rules. And then with the normal distribution problem that we tried, right? That was a continuous random variable. So it doesn't matter, both discrete and continuous random variables. All right, that's all I have for you guys. Thank you so much for watching. Have a great day.